Hi, so today we're going to talk about chapter 2, which is the chemical basis of life. So basically connecting chemistry and biology together. And so this is going to include four main topics. The first one is matter, atom, and molecule, so defining what exactly matter is. And then from there, moving on to how do these atoms and molecules interact together to form different type of bonds. And one of the bonds that's really important that we look at is hydrogen bond. So with that, we're going to be looking at the importance of water, because water molecules combine together, or they bond together because of hydrogen bonds, and it plays a big role with regards to the impact of how important water is on Earth, right? Recall that the majority of Earth is covered by water. And then the last topic we're going to talk about is pH. So let's move on to matter. So what do we mean by matter? What is matter? Well, matter is pretty much anything that takes up space. And matter can exist in three different types of state. It can be solid, it can be liquid, and it can be gas. So as you can see, solid, so one easy way to kind of demonstrate this, right, is water, because we can see that water exists in all three states. So we have our solid, which you could think of as ice, right? So ice is nice and solid. But then water can also transition to liquid, and you guys are familiar with liquid. So liquid the difference between solid and liquid is solid has a fixed shape and a fixed volume, right? So ice holds whatever shape your ice mold happen to be. So if you put it in a mold that looks like a pumpkin, it's going to have the shape of a pumpkin. But as it melts and becomes liquid, it takes the shape of its container. So it doesn't have that rigid fixed surface and volume as we expect. And our last one is gas. Well, gas, when water is really heated and you see it vaporizing, right, it turns into a gas molecule. And that also takes shape of a container and a volume. And a lot of times we don't think of gas as being matter and taking up space, but it does, right? So if you just wave your hands in front of you, you can feel like those gas molecules kind of moving around, right? And so we think of these as different type of states of matter. And we're also going to touch upon elements. So you might recall from high school biology or chemistry that periodic table of elements. Well, elements are any substance that cannot be broken down into another substance by ordinary chemical means. So like oxygen, one atom of oxygen is an example of an element, right? We can't break that oxygen into anything smaller. Whereas water is, you probably heard H2O, right? So we can actually break that H2O into hydrogen and oxygen. So that's the difference between element versus atom. So let's move on to the different type of elements that are actually in the human body. So there are currently 58 different elements that make up the human body. Right, and so here we can see over here all the different elements that we're talking about. And the four major elements that make up most of our body weight is carbon, hydrogen, oxygen, and nitrogen. So those are the four. We have other elements in our body. For example, even though arsenic is considered, for example, I'm going to move my head out of the way. Arsenic is considered super toxic. We actually have a small amount that's actually in our body. Is only when we have an extensive over a certain threshold that it becomes really toxic for our body, right? And interestingly, if you actually put a cost on our body, like when they always say, like, what is the value of a human life? Well, I guess technically our body is worth $160. I guess that wouldn't include our soul, but all of the elements in the human body, if we were actually to manufacture it, would equal about $160. Cheaper than a pair of Apple headphones. Okay, let's move on. Sorry, I'm moving down. So elements are considered atoms, right? So what are atoms? Well, atoms are the actual building block of all substance. And an atom is made of proton, which we have right here, is made of neutrons, which we have right here, these ones, and it's also made of electrons, which would be these guys right here, right? So we have protons and neutrons right here, and our electrons right here. And so protons, as you can see, has a positive charge, while neutrons have a negative charge. Neutrons have a neutral charge, neutral charge, and electrons have a negative charge. You can see the negative right here. And electrons actually circulate around the positive and the neutral charge here. So they actually circulate around the proton and the neutrons. And so when we actually look at atoms, move myself here. When we actually look at atoms, they differ based on their subatomic particles. That is, their proton, their neutrons, and their electrons. Right? That's how they differ between them. And so the atomic number, when we're trying to determine what element it is that we're actually looking at, is based right here. This is atomic number based on the number of protons that you actually have in that element. So for example, hydrogen, which I just circled right here, has 1 proton. So all hydrogen molecules have 1 proton, right? Once you have 2 protons, we're no longer hydrogen anymore. Now we are helium. So carbon, for example, you can see right here 6. So it has 6 protons. So my question to you is, what is the atomic number of boron, which is B? So it's this guy right here. Well, it's going to be 5, right? So if it has 5 protons, it also means that it has 5 electrons. Because in an atom, the number of protons is equal to the number of electrons, I should say, is equivalent to the number of protons that's in that atom. So I said we can't have a different number of protons. Carbon always has 6 protons. So can carbon actually have a different number of neutrons? Well, they can, because we can actually have different isotopes of the same element. And so in that case, we can have varying numbers of neutrons, even though the protons is equivalent in each one of these elements, right? So carbon is an example of that. So carbon, on the table of the periodic table, if we were looking at it, it has 6 proton, 6 neutron. However, you might have heard of carbon dating, for example. So carbon dating, we're actually looking at an isotope of carbon. So we're actually looking at carbon-14. And while it has 6 proton, it actually has 8 neutrons. So with that, because protons and neutrons actually have because they're matter and they actually have a weight to it, the mass number that we're looking at is equivalent to 6 plus 8. So it's equivalent to 14 here, which is why this is carbon-14. So this is actually its mass number here. Whereas carbon-12 has 6 proton and 6 neutron, so its mass number is actually 12. So mass number is the total number of proton and neutron in a nucleus, and it's how we go about identifying different type of isotope. So here we have 3 different versions of the element carbon. We have carbon-12, carbon-13, and carbon-14. And you can see that across the board, there's an equivalent number of protons, but we actually have different number of neutrons for each one of these different isotope of carbon. So let's kind of look through these questions and see if we can figure them out. So how many protons does carbon-16 have? Well, carbon-16 is going to have, I'm going to try to write with this pen, it's not super easy, 6 proton. I'm trying to write P, sorry guys. This is not, if anybody has suggestions for how better to write, I'm trying to use a magic trackpad, just to let you know right now, and a pen, and it's not working very well. I'm able to do it, but it's super slow. Anyway, let's go back to this. Okay, so carbon-16 has 6 proton, right? So how many neutrons does it have? Well, we know that the mass number is 16, and it has 6 proton. So 16 minus 6 means that it has 10 neutrons in it. Right? Okay, so based on that, we know that mass number is based on protein and neutron. So what is the mass number of an atom that has 8 protons and 12 neutrons? Well, 8 plus 12 is what? It's going to be 20. So this would be the mass number. And if we go back to the periodic table, we can see which element that is. So what did we say? It was 8 before? So that would be oxygen that we're looking at, right? Because it has 8 right here. So oxygen would be, well, that wasn't a very good circle. Oxygen would be the element that we're looking at here. So this would be oxygen 20, like if we were to actually identify it. So why am I even talking about isotope? Why do we care about isotope? We actually use isotope for a lot of different things. So one of the things that I mentioned that we use it for is carbon dating. So we can actually look at different fossil records and determine how old they are based on the decay of carbon, the carbon isotope, the C14, as it returns back down to C12. And so based on the different percentage of different isotope that we have of carbon, we can actually, from there, infer how old we think that fossil is. Another thing that we use isotope a lot for is actually radioactive. So this is an image of a scan, where we use radioactive isotope as a tracer. And so by using isotope tracer, this isotope is, like as the name implies, radioactive. So it's very active. So it is actually providing this different heat right here that we're seeing. So this color is indication of heat. And as you're using this tracer, you can actually see where it migrates to based on the heat that's released. Radioactive isotope can also be used to actually sterilize medical equipment because it's just very high energy. So we can actually also use it to sterilize our medical equipment. Okay, so why are we talking about this chapter at all? Why are we talking about electrons? Well, electrons are really important because it is how atoms are able to actually share, acquire, or donate electrons between each other. So here we have an example, and we'll talk about this a little bit more when we talk about bonds, but we have an example of sodium and chloride, right? So when they're separate, sodium will actually have this positive charge and chloride will actually have this negative charge, but together they can actually share this electron right here and combine together to form what we know as salt. Same thing with water here. You have hydrogen, which normally has 1 electron, and we have oxygen over here, right? And you can see that oxygen is normally would have 7, and we actually want to have, for a electron to be happy or element to be happy, it wants a full shell, and 8 is considered a full shell. So it wants to share electrons. Sorry, it has 6. It normally has 6, not 8, 7. It normally has 6, and it will share 1 electron over here with this hydrogen and 1 electron over here with this hydrogen, right? The hydrogen is actually donating the electron over to oxygen, and together it now has a full shell of 8. So when the atoms are interacting with each other, it's based on how much electron they have. And they're happier, as I said, when they have a full shell. So, sorry, so I misspoke. Oxygen normally has 6 electrons around it. And it is going to gain an electron from bonding with 2 molecules of hydrogen. Okay, so atoms and ions. Ions have a positive and a negative charge, and this is gonna play an important role when we actually look at how they can gain or lose an electron. So when I was talking about the shell earlier, I was talking about the valence shell, which is the most outermost shell right here. So in the outermost shell, we want to have a full outermost shell. And it can vary depending on the level of shell. The most inner one you can see has 2, but typically for what you guys are going to be looking at, we're looking at a full valence shell would mean 8 electrons. So we want to have 8 electrons in order to be happy. Okay, so we're going to be looking at bonds in our next section right here. So when we have the interaction between these different ions, the positive and the negative ions, that's when we can actually form different type of chemical bonds. And it is this chemical bond and the force between them when the electron adds that will actually allow us to actually start forming molecules. So let's stop here, and we're going to come back and talk a little bit more about molecules and how molecules can form compounds and so on as we look at different type of bonds.